You are holding a clock. It is the most precise instrument ever constructed by human hands. A machine of chilled atoms and laser light that loses 1 second every 300 billion years, a span of time more than 20 times the current age of the universe. Every tick is calibrated to the vibration of electrons inside ytterbium atoms, a rhythm so steady, so relentless, that engineers have to correct it for the gravitational pull of the floor beneath it. It has never been wrong by more than a single heartbeat across the entire lifetime of every star you can see tonight. And physicists have now discovered that it has a flaw, not in the engineering, not in the atoms. In time itself, the flaw is tiny, vanishingly, almost insultingly small. But the reason it exists, the reason it must exist, reaches into the deepest unresolved crisis in all of physics. It touches the question of why yesterday existed before today. It connects to a problem that has kept the greatest minds in the history of science awake in the small hours, staring at equations that refuse to agree. The flaw is not in your clock. The flaw is in the universe's ability to know precisely when anything is happening at all. There is a building in Gaithersburg, Maryland, that governs time for most of the modern world. It sits inside a federal research campus, unremarkable from the outside, a low, climate-controlled structure surrounded by manicured lawns and security fencing. Inside, however, it houses something that every smartphone, every air traffic control system, every financial transaction, every satellite in low Earth orbit depends upon with absolute, unconditional trust. The National Institute of Standards and Technology, NIST, is the keeper of official time in the United States, and its atomic clocks are not merely accurate. They are accurate in a way that strains the human imagination to comprehend. The current record holder, a strontium optical lattice clock built at Gila, the joint institute operated by NIST and the University of Colorado, would lose 1 second across 300 billion years of continuous operation. Let that settle for a moment. The universe, as best we can measure it, is approximately 13.8 billion years old. This clock would need to run for more than 21 complete lifetimes of the universe before it drifted a single second from true time. Its ticks are referenced to the frequency at which strontium atoms absorb laser light, a frequency of 429,228,229,873 vibrations per second. Not approximately, exactly. Every measurement is calibrated against this number. We built this because we had to. The GPS system your phone uses to navigate a junction would be inaccurate by roughly 11 kilometers per day without relativistic corrections applied to the atomic clocks aboard its satellites. The global financial system executes trades timed to fractions of a microsecond, where a single errant tick can be worth millions. Medical imaging equipment, gravitational wave detectors, intercontinental navigation, all of it rests on the assumption that time is something we can measure without limit, that with enough ingenuity and enough engineering, we can keep sharpening our clocks indefinitely toward perfect precision. That assumption, it turns out, may be wrong, not because our engineering is imperfect, not because atoms misbehave or lasers drift, but because the universe itself, at its most fundamental level, may not permit time to be perfectly smooth. There may be a tremor built into the fabric of time, an irreducible jitter, smaller than anything we have ever measured, imposed not by technology, but by the deepest laws of physics. This is a story that begins, as so many of the most consequential stories in science begin, with a question that sounds deceptively simple. What exactly is time? Not as a philosophical reverie, not as a poet's meditation on loss and memory, but as a physical object. Something that can be weighed, measured and, as we are about to discover, perhaps found to be subtly imperfect. The first thing to understand is that physicists do not agree on what time is. This is not a fringe controversy or a debate confined to philosophers. It is one of the central unresolved crises of modern theoretical physics, our two greatest frameworks for understanding the universe, quantum mechanics and general relativity. Each describe time in a fundamentally different way, and the two descriptions are mutually incompatible. We have known about this incompatibility for nearly a century. We have not solved it. Quantum mechanics treats time as an eternal, featureless backdrop, a perfect abstract stage on which all quantum events are performed. Time in quantum mechanics does not interact with matter. It cannot be measured by a quantum system. It cannot be affected by the presence of particles or fields. It simply flows uniformly and without interruption, as an external clock that governs the rate at which quantum systems evolve. This is a useful fiction. It produces predictions of extraordinary precision, but it is a fiction nonetheless, because we know from another framework entirely that time is no such thing. General relativity, Einstein's theory of gravity, describes time as a physical dimension of space-time itself, a dimension that bends, stretches, and warps under the influence of mass and energy. Clocks run slower in stronger gravitational fields. Two clocks at different altitudes, separated by as little as 1 centimetre, tick at measurably different rates. Time is not an external stage in general relativity. It is part of the scenery. It is as physical as a rock, and near a black hole, or at the moment of the Big Bang, it becomes something stranger still. These two descriptions of time cannot both be completely correct. They cannot both be fundamental. And the question of which one to sacrifice, or how to reconcile the two, is the deepest unsolved problem in all of physics. What the team from Rome and Budapest found in 2025 is that the answer to this question may leave a fingerprint on time itself, a tiny flaw, a tremor, something that no clock ever built can detect, but that, in principle, no clock ever built could be shielded from. It begins as almost everything strange in modern physics begins, with the quantum, and with a cat. In 1935, Erwin Schrödinger published a thought experiment that he intended as a reductio ad absurdum, a demonstration that quantum mechanics, in its standard interpretation, produced conclusions so manifestly absurd that the theory must be incomplete. He imagined a cat sealed inside a steel box, connected to a device that would release a lethal dose of poison if a radioactive atom, governed by quantum probability, happened to decay within a set period of time. In the framework of standard quantum mechanics, before anyone opens the box, the atom exists in a superposition of decayed and not decayed states simultaneously. Therefore, by the logic of the theory itself, the cat must also exist in a superposition of alive and dead simultaneously. Schrödinger found this conclusion monstrous. The cat is either alive or it is dead, he insisted. Not both. The theory must be missing something. He presented this as a failure of the Copenhagen interpretation. The orthodox reading of quantum mechanics that treats the wave function as a complete description of reality and defers the question of what causes it to snap into a single definite state to the act of measurement. What Schrödinger could not have known was that 90 years later, physicists would still be arguing about this, not with less urgency than before, with considerably more. The measurement problem, as it has come to be known in the literature, remains unresolved. It is not a peripheral question. It sits at the very heart of what quantum mechanics means, and the answer you give to it turns out to have profound consequences for the nature of time itself. Here is the problem stated with maximum clarity. The Schrödinger equation, the fundamental equation of quantum mechanics, describes how a quantum state, its wave function, evolves over time. It evolves smoothly, continuously, reversibly. If you run a Schrödinger evolution forward in time and then backwards, you get exactly back to where you started. There is nothing in this equation that privileges one direction of time over another. It is, in the technical language of physics, time symmetric. This means that quantum mechanics, at the level of its fundamental equation, has no arrow of time. Time could run in either direction, and the equation would be satisfied. But when you measure a quantum system, when you actually look at it and record a result, something very different happens. The smooth, continuous, reversible evolution stops. The wave function collapses instantaneously from a smeared-out superposition of possibilities into a single definite outcome. This collapse is not described by the Schrödinger equation. It is an additional postulate bolted onto the theory from outside that says something happens during measurement that the equation does not describe, and whatever that something is, it is irreversible. You cannot uncollapse a wave function. The collapse goes one way only, forwards. This is what makes it so philosophically significant. The Schrödinger equation is reversible. The collapse is not. The collapse has an arrow of time, a direction from possibility to actuality, from quantum uncertainty to classical fact, that points irreversibly from past to future. If this collapse is real, if it is a physical process and not merely an epistemic update in an observer's mind, then the act of quantum measurement is one of the genuinely time asymmetric processes in nature. And that raises an immediate, urgent question. What causes it? The standard Copenhagen interpretation of quantum mechanics essentially refuses to answer this question. It says that the wave function is a tool for calculating probabilities. When you measure the system, you get a result. The wave function updates accordingly. Do not ask what the wave function is between measurements. Do not ask why measurement causes collapse. The theory works, use it. For generations of physicists focused on calculation rather than foundations, this was a perfectly adequate response. The Copenhagen interpretation is, in a practical sense, the most successful scientific framework in human history. Quantum mechanics underpins semiconductors, lasers, MRI scanners, solar cells, and the entire digital economy. It has been tested to a precision greater than any other theory ever produced. Its predictions have never been wrong, but it leaves a hole in the middle of physics large enough to drive a cosmological crisis through. And that crisis is not merely philosophical, it is physical, because if we do not know what causes wave function collapse, if we cannot say whether it is a real physical process or a mathematical fiction, then we do not fully understand the laws of nature. And if we do not understand the laws of nature at this level, then we do not understand why time moves in the direction it does. This is what I find one of the most genuinely profound puzzles in all of science. We use quantum mechanics every day. We trust it with aircraft navigation, with cancer treatment, with every microchip in every device you own. And we do not, at the foundational level, know what it means. We have a machine that works perfectly, and we cannot explain why the machine works. The various attempts to explain wave function collapse fall broadly into three camps. The first camp says collapse is not real at all. What appears to be collapse is simply the branching of reality into parallel worlds, each of which experiences a different outcome. This is the many worlds interpretation, proposed by Hugh Everett in 1957. It is elegant, and it preserves the perfect time symmetry of the Schrödinger equation. But it pays for this elegance with an infinity of unobservable universes, which strikes many physicists as too high a price. The second camp says collapse is a result of environmental decoherence, the process by which quantum systems, upon interacting with their environment, lose their coherent superposition and appear classical from the outside. Decoherence is real, experimentally confirmed, and explains a great deal of why quantum effects are not visible at macroscopic scales. Decoherence alone does not explain why any single definite outcome occurs rather than another. It explains why the alternatives become practically unobservable. It does not explain why only one of them is real. The third camp is the most radical, and the most relevant to our story. It says that collapse is a real physical process, that the wave function literally snaps from superposition to definiteness, and that this snap is caused by something we have not yet identified, something outside standard quantum mechanics, something that might, if several decades of theoretical development are correct, be related to gravity. This third camp has a name. They are the spontaneous collapse theorists, and what they found in the autumn of 2025 illuminated something about time that nobody had expected to see. The idea that wave function collapse might be a real physical process, not an interpretational choice, but an actual event governed by new physics, has been developing for over 4 decades. It did not begin with a dramatic announcement or a single eureka moment. It began, as most of the best ideas in physics begin, with a small number of people who were dissatisfied with the prevailing consensus and willing to calculate the consequences of their dissatisfaction. In 1975, a young Italian physicist named Giancarlo Ghirardi was teaching a course on quantum mechanics at the University of Trieste and finding himself increasingly unable to answer his students' questions about what precisely wavefunction collapse was. Not as metaphysics as physics. His students wanted to know the mechanism. They wanted to know the equations. The Copenhagen interpretation told them not to ask. Gherardi found this unsatisfying in a way that became obsessive. Over the following decade, he collaborated with Alberto Rimini and Tullio Weber. The group would come to be known as GRW, from their initials, on a proposal so strange that the physics community initially dismissed it as philosophical indulgence. Their idea was simple in principle and radical in implication. What if the Schrödinger equation was not exactly right? What if there was an additional spontaneous term in the equation that caused the wave function to collapse randomly, without any trigger, without any measurement, without any observation, simply because the universe had built into its equations a stochastic probabilistic tendency for quantum superpositions to snap into classical states? The GRW theory proposed that individual particles undergo spontaneous collapse, a sudden random localization in space, at a rate so fantastically slow that for a single isolated particle you would have to wait roughly 100 million years for one collapse event. But for a macroscopic object consisting of 10 cubic or more particles, the mathematics changed dramatically. Because in the GRW model, when any single particle in a composite system collapses, it drags the entire entangled system with it. For an object containing as many particles as a grain of sand, the collapse rate becomes so rapid, effectively instantaneous compared to any timescale of human experience, that the object is never in superposition for long enough to exhibit quantum behavior. The theory explained, with a single modification to the Schrödinger equation, why quantum effects disappeared at the macroscopic scale, not because of measurement, not because of observers, because of physics. The GRW model was the founding document of what would become the field of spontaneous collapse models, or objective collapse theories, and it generated, over the following decades, a community of physicists who took the measurement problem seriously as a physical problem and dedicated their careers to solving it with equations rather than interpretation. In 1987, a Hungarian physicist working in Budapest published a paper that would extend the GRW idea in a direction that nobody had fully anticipated. His name was Lajos Diósi, and his proposal was characterized by a kind of audacious parsimony that marks the best theoretical physics. Diósi noticed that GRW required a free parameter, a rate of spontaneous collapse that had to be inserted by hand, adjusted to fit the requirement that macroscopic objects behave classically, while quantum objects remain in superposition. Where did this rate come from? GRW had no answer. Diósi asked whether there might be a natural physical process that could generate spontaneous collapse without any adjustable parameters. A process universal enough to apply to everything, fundamental enough to be derived from first principles rather than inserted by hand. He proposed that the answer was gravity. Specifically, that the spontaneous collapse of the wave function was caused by the gravitational interaction between a quantum object and its own mass distribution, a kind of gravitational self-interaction that, for sufficiently massive objects, became too unstable to sustain a superposition, and forced the system to select a single definite position. The collapse rate in Diósi's model was not a free parameter, it was determined by Newton's gravitational constant. The theory was, in its own terminology, parameter-free. The only input was physics we already knew. This was the Diósi-Penrose model in its embryonic form, though at this stage it bore only Diósi's name. The Penrose contribution came 3 years later, independently, and from a perspective so different that the convergence of the two proposals was itself striking enough to prompt serious attention. Roger Penrose, by 1989, was among the most celebrated theoretical physicists in the world. His contributions to mathematical physics were staggering in their variety. Singularity theorems co-authored with Stephen Hawking, the discovery of Penrose tilings, contributions to twistor theory, and the mathematics of spacetime. He was a thinker whose range was, and remains, essentially without peer in his generation. And in a book published that year, The Emperor's New Mind, Penrose outlined a proposal that arrived at almost exactly Diósi's conclusion by a completely different route. Penrose argued from the principles of general relativity. In general relativity, the position of a massive object determines the geometry of space-time around it, the curvature, the warping of time and space that we call gravity. Now consider a quantum superposition in which a massive object is simultaneously in two different positions. In state A, the object is here, and space-time is curved accordingly. In state B, the object is there, and space-time is curved differently. In a genuine quantum superposition, both states coexist simultaneously, but that means two incompatible space-time geometries coexist simultaneously. And this, Penrose argued, was a form of gravitational instability that the universe could not sustain. At some point, at a moment determined by the magnitude of the space-time difference between the two states, the superposition becomes gravitationally untenable, and the system is forced to resolve into one state or the other. Penrose called this process objective reduction. Not triggered by measurement, not triggered by observation, triggered by the mismatch between quantum superposition and gravitational reality, triggered by a fundamental incompatibility between quantum mechanics and general relativity that plays out not at the scale of cosmology or black holes, but at the scale of any sufficiently massive quantum object, which, for a large enough object, could mean objects as small as certain proteins or molecular assemblies. The convergence of Diósi and Penrose from different starting points on the same conclusion was not lost on the physics community. The Diósi-Penrose model, as it came to be known, placed gravity at the centre of the measurement problem. It proposed that the classical world emerges not from decoherence alone, not from many worlds, not from arbitrary measurement, but from a gravitational intervention, the universe using its own geometry to collapse quantum superpositions before they become physically inconsistent. Now, here is where the story becomes urgent. Because if this model is right, if gravity really does cause wave-function collapse, then it has consequences that go well beyond the measurement problem. If space-time geometry is involved in collapse events, then those collapse events affect space-time geometry. Every quantum collapse is a gravitational event, however infinitesimal. And gravitational events involve time dilation, time curvature, the very metric of space-time that defines the intervals we call seconds. This was the thought that led a PhD student in Rome, in the early months of 2025, to ask a question that turned out to have a deeply unsettling answer. What does spontaneous quantum collapse imply for the precision of time itself? The Diósi-Penrose paradox was not fully named until Nicola Bortolotti sat down with his collaborators to formalize what they were calculating. But the problem it describes had been implicit in the literature for decades, waiting for someone precise enough, patient enough, and technically equipped enough to pull it fully into the light. The paradox, stated simply, is this. If gravity causes quantum collapse, and quantum collapse involves fluctuations in space-time geometry, and space-time geometry defines what time is, then the process of quantum collapse must introduce a fundamental uncertainty into the measurement of time itself. Not a technological uncertainty, not a quantum uncertainty in the mechanical parts of a clock, a more basic uncertainty, an uncertainty in the very substrate in which time exists, a tremor in the fabric, and that tremor, however small, means that no clock can ever be perfect, not because the clock is flawed, because time is. To understand what Bortolotti and his team actually calculated, and why the result was, as Bortolotti himself described it, surprisingly reassuring and yet philosophically staggering, it helps to understand exactly what a clock is measuring when it measures time. An atomic clock does not measure time directly. No instrument measures time directly because time is not an object you can insert a probe into. An atomic clock measures frequency. Specifically, it measures the frequency of electromagnetic radiation, laser light or microwave radiation that corresponds to a transition between two precisely defined energy levels of a specific type of atom. For the cesium atoms used in the primary frequency standard, this transition frequency is exactly 9,192,631,770 oscillations per second. The second, as currently defined, is the time it takes for 9,092,631,770 such oscillations to occur. For ytterbium optical lattice clocks, the relevant transition is in the optical range, with a frequency of approximately 518,295,836,590,864 cycles per second, a number so large that the clock effectively checks itself against reality more than half a quadrillion times every second. What makes these clocks so precise is precisely this stability of the reference frequency. Atoms do not drift, they do not age, they do not respond to pressure, temperature, or humidity in ways that alter their fundamental transition frequencies, or rather they do slightly, and the extraordinary engineering challenge of modern atomic timekeeping is to eliminate or characterize and correct for every such perturbation. The goal is a reference that counts against absolute physical law rather than against any contingent, engineered system. But the absolute physical law the clock is counting against is quantum mechanics. The transition frequency is a quantum mechanical quantity determined by the quantum energy levels of the electron in the atom, and the measurement of this frequency requires the atom to interact with the clock's electromagnetic field. Requires, in other words, a quantum measurement event, a collapse. This is the entry point for Bortolotti's calculation. If wavefunction collapse involves space-time fluctuations, if every collapse event is accompanied by a tiny disturbance in the metric of space-time, as the Diósi-Penrose model implies, then the act of measuring time with an atomic clock involves inherently a process that disturbs space-time, and a disturbed space-time is a space-time in which the interval we call a second is not perfectly constant. The fluctuations are overwhelmingly smaller than anything we can measure, but they are not zero. What Bortolotti and his colleagues, Catalina Curcianu, Christian Pichicchia, Lajos Diósi himself, and Simone Manti did in their paper published in Physical Review Research in November 2025 was to establish, for the first time, a precise quantitative relationship between the parameters of quantum collapse models and this fundamental limit on clock precision. They worked with two models, the Diósi-Penrose model and a second model called Continuous Spontaneous Localization, or CSL, originally proposed by Philip Pearl in 1989. The CSL model is the most mathematically developed of all spontaneous collapse theories. A GRW proposed discrete instantaneous collapse events occurring at random intervals. CSL describes a continuous, ongoing process in which the wave function is perpetually nudged by a background stochastic field, a universal noise that randomly localizes quantum systems towards definite positions on a continuous basis. The CSL model has a profound formal similarity to the mathematics of decoherence, but with a crucial difference, where decoherence is unitary, preserving the full quantum state in a larger environmental system. CSL is non-unitary. Information is genuinely lost during CSL collapse. The evolution is irreversible. What Bortolotti's team showed was that when you take the CSL model seriously, when you accept that this background stochastic field is real, not just a mathematical convenience, and when you ask what this field does to space-time, given the Diósi-Penrose connection between collapse and gravity, the answer is unambiguous. The stochastic collapse field generates fluctuations in the space-time metric. These fluctuations are tiny, of order 10⁻33 seconds in absolute magnitude, or roughly 10 billion times smaller than the Planck time of 5, 39 times 10⁻44 seconds, but they are non-zero, and because they are generated by a fundamental physical process rather than any engineered imperfection, they constitute an absolute flaw on the precision of any time measurement. The Planck time, to put this number in perspective, is already considered the smallest physically meaningful interval of time. It is the time it takes light to travel one Planck length, approximately 1.616 times 10⁻35 meters, the scale at which quantum gravitational effects are believed to become dominant. The The fluctuations predicted by Bortolotti's team are smaller than this. They are so small that even the most ambitious future technology we cannot currently conceptualize, operating on physical principles we have not yet discovered, would struggle to reach the scale at which they would become measurable. But here is what makes this result important in a way that transcends the question of clock precision. The existence of this fundamental limit, even at this infinitesimal scale, is not a technological failure. It is a fingerprint of the universe's deepest architecture. It says that time is not smooth. It says that time is not an external, featureless backdrop. It says that time participates in physics, that it is affected by the processes it ostensibly governs. And it says that our two great theories of nature, quantum mechanics and general relativity, are not merely mathematically incompatible. They are already leaving traces of their incompatibility in the very instrument we use to measure time. I find this genuinely haunting, not because it means our clocks are broken, they are not. Not because it affects any technology we use today or will use in any foreseeable future. It does not, but because it suggests that the smooth, featureless, perfectly reliable thing we call time is, at some level, too deep to reach, not perfectly smooth at all. That our most fundamental assumption, that the universe ticks evenly, that the passage of time is the one thing we can count on absolutely, is an approximation, a very, very good approximation. But an approximation, the question this raises, is one that cuts to the bone of physics. If time is not perfectly smooth, if it trembles, even infinitesimally, what is causing the trembling? And the answer to that question requires us to go back, further than quantum mechanics, further than general relativity, all the way to a puzzle that has been waiting at the heart of physics since 1927. Why does time point in only one direction? There is a village in Kendal, in the English Lake District, called Burneside. In the early years of the 20th century, it was the kind of place where a certain species of intellectual Quaker family took root, quiet, bookish, committed to education in a way that was almost devotional. Arthur Stanley Eddington was born not far from there in 1882, and he carried something of that quality throughout his life. He was not a flamboyant man. He was famously taciturn in social situations, often retreating into an interior world that colleagues found difficult to read. But when he wrote, when he chose to explain his science to the wider world, something extraordinary happened. The prose became almost poetic. It was Eddington, in his 1927 book, The Nature of the Physical World, who first coined the phrase that would define one of the deepest problems in physics. He called it the arrow of time. He meant by this the asymmetry of temporal direction that is experienced by every conscious being and observed in every macroscopic physical process. The fact that time seems to flow in one direction only, from past to future, from yesterday to tomorrow, from the broken egg on the kitchen floor to the unbroken egg in the refrigerator, and never in reverse. Eddington chose the metaphor carefully. An arrow has a head and a tail. It points in one direction. Remove it from its physical context, and you cannot tell which end came first from the geometry alone. You have to know which end is sharp. Time is like this. The equations of physics, as he observed, do not intrinsically distinguish past from future at the microscopic level. A film of two billiard balls colliding, run backwards, is indistinguishable from the same film run forwards. The same is true of two electrons scattering, or a photon being absorbed and re-emitted, or virtually any fundamental physical interaction at the microscopic scale. The laws of physics, as written in the language of fundamental equations, are time-symmetric. They work equally well in both temporal directions. And yet no one watching a film of a glass falling from a table and shattering on the floor would mistake the reversed film for real. The pieces do not leap up and reassemble. The shards do not coalesce into a glass and return to the table. This asymmetry, the one that distinguishes the future from the past at every scale of ordinary experience, has no counterpart in the fundamental equations. It is emergent. Somehow the universe produces, from time-symmetric microphysics, a profoundly time-asymmetric macro-world. How? Eddington knew the thermodynamic answer, the one that had been developed by Ludwig Boltzmann in Vienna in the 1870s. Entropy, the measure of disorder in a physical system, always increases in an isolated system. Heat flows from hot to cold, not from cold to hot. Smoke disperses, it does not congregate. Information becomes more scrambled, not more ordered. This is the second law of thermodynamics, the statement that the total entropy of a closed system never decreases. And entropy, Boltzmann showed, is a statistical property. High entropy states are simply vastly more probable than low entropy states, in the same way that a shuffled deck of cards is vastly more probable than a perfectly ordered one. Time's arrow in this view points toward increasing entropy, because increasing entropy is the overwhelmingly probable direction of evolution for any macroscopic system. This is the right answer as far as it goes. It is the standard answer. But Eddington, with the characteristic precision that marked his thinking, immediately noticed that it was incomplete. Because Boltzmann's argument assumed a starting point of low entropy, it assumed that the past was a state of unusual order, a state so unlikely that any subsequent evolution would almost certainly move toward greater disorder. This assumption is, as far as we can tell, correct. The early universe was in a state of extraordinarily low entropy, a condition of pristine uniformity that was, in an entropic sense, almost impossibly special. The expansion of the universe, the formation of stars and galaxies and planets and life, the entire history of cosmic evolution, all of it is the universe inexorably moving from that improbably ordered initial condition toward the higher entropy states that statistics predicts. But why was the early universe in such a low entropy state? Boltzmann's argument does not explain this. The second law tells you that entropy will increase from wherever you started. It does not tell you why you started in a place of such remarkable order. This is what philosophers of physics call the past hypothesis, the brute assumption that the initial state of the universe was very special, very low in entropy, for reasons that the second law itself cannot account for. It is, in a meaningful sense, the deepest unanswered question about time, not merely why time points forward, but why the universe began in the kind of state from which a temporal arrow could emerge at all. Eddington understood all of this, and he went further. He pointed out that the thermodynamic arrow of time and the psychological arrow of time, our subjective experience of the present moving toward the future, our sense of time flowing rather than simply existing, were not obviously the same thing. The thermodynamic arrow is about entropy. The psychological arrow is about consciousness and memory and the felt sense of duration. The electromagnetic arrow, which describes why radiation spreads outward from a source rather than converging inward upon it, is yet another arrow. And there is the cosmological arrow, the fact that the universe is expanding rather than contracting, that cosmic time runs in the direction of increasing scale factor. Are all of these arrows the same? Do they all point in the same direction for the same reason? Or are they distinct phenomena that happen to be aligned? These questions, which Eddington raised in 1927, have not been definitively answered nearly a century later. They remain open, and they are intimately connected to the question of what wave function collapse is, how it relates to gravity, and why Bortolotti's team found what they found in the autumn of 2025. Because if wave function collapse is real, if it is a physical process governed by the equations of spontaneous collapse models, then it adds a new arrow to Eddington's taxonomy, the collapse arrow, the direction from quantum superposition to classical definiteness, from possibility to actuality, that is built into the irreversible dynamics of the collapse process. And the collapse arrow points in the same direction as all the others, forward, toward the future, toward higher entropy, toward greater disorder, toward the asymmetric half of the universe's story that we call history. The coincidence, if it is a coincidence, is striking enough to suggest something deeper is going on, and that deeper thing, whatever it is, may be what leaves the tremor in time that Bortolotti's team calculated. But before we can understand the full significance of what they found, we need to meet the man whose name is on one of the two models that produced the result. We need to understand how a physicist in Budapest, working in relative isolation during one of the most turbulent periods in Eastern European history, arrived at an idea that connected gravity, collapse and time, and found, decades later, that his equations had been more right than even he had dared to claim. Lajos Diósi was born in Budapest in 1950. He trained as a physicist at Eötvös Loránd University, one of Hungary's most distinguished scientific institutions, during the years of Soviet-influenced restriction that shaped the careers of an entire generation of Central European scientists. Physics, in this environment, had a quality of refuge about it. The equations did not care about political borders. The Schrödinger equation was equally true in Budapest and in Cambridge. And within the walls of theoretical physics, a kind of intellectual freedom persisted that the broader culture did not always permit. Diósi's early career was focused on open quantum systems, the study of how quantum systems interact with their environments, losing coherence and behaving increasingly classically. This was, in the 1970s and early 1980s, a productive but still somewhat marginal field within quantum mechanics, one that would not come to full prominence until the development of quantum information science in the 1990s. Diósi was working on the mathematics of quantum dissipation, on the stochastic equations that governed the evolution of quantum states in the presence of environmental noise, when he encountered a question that would redirect his research for the rest of his career. The question was, again, the measurement problem. Why did measurement cause collapse? And was there a way to write down the equations of a physical collapse mechanism that was consistent with both quantum mechanics and gravity? His 1987 paper, published in Physics Letters A, introduced the model that would bear his name. It was a remarkable document, technical, densely mathematical, and in its conclusions strikingly bold. The abstract promised, and the paper delivered, a universal master equation for the gravitational violation of quantum mechanics. Not a philosophical proposal, not an interpretation, an equation, one that could in principle be tested. The equation was austere in its elegance. It said that a quantum superposition of two states differing in their mass distribution would collapse spontaneously at a rate inversely proportional to the gravitational interaction energy between those two mass distributions. The more gravitationally incompatible the two states, the more different their space-time geometries, the faster they would collapse into one or the other. For a single atom, the collapse would be so slow as to be unobservable across cosmological timescales. For a macroscopic object, it would be effectively instantaneous. The paper did not receive immediately the attention it deserved. It was published in a journal read primarily by specialists in mathematical physics, in a country whose scientific output was still under the shadow of Cold War isolation. It was not until Roger Penrose arrived at essentially the same conclusion, from a completely different angle, that the scientific community began to take the gravitational collapse hypothesis seriously as a research program rather than as an eccentric outlier. Roger Penrose encountered Diósi's work in the early 1990s, and his response was characteristic of the man. He immediately extended it, challenged it, and wove it into a much larger framework of ideas about consciousness, computation, and the nature of quantum reality. The Penrose contribution to the model was not primarily mathematical, Diósi had done that work, but physical and conceptual. Penrose argued, in Shadows of the Mind, 1994, and in subsequent lectures and papers, that the gravitational collapse of the wave function was not merely a feature of quantum mechanics. It was a window into a deeper theory of physics that did not yet exist, a theory in which quantum mechanics and general relativity were reconciled, and in which the collapse process was as fundamental and as lawful as any other physical interaction. For Diósi, the Penrose endorsement was transformative, not in terms of his confidence in the model. He had always believed in it, but in terms of its reception by the broader community. By the mid-1990s, the Diósi-Penrose model had become one of the standard targets for experimental tests of objective collapse, laboratories around the world began designing tabletop experiments to search for the gravitational decoherence that the model predicted. Experiments using levitated nanoparticles, crystal oscillators, ultra-cold atom arrays, any system large enough to exhibit macroscopic superposition for long enough to be sensitive to gravitational collapse effects. None of these experiments has yet definitively confirmed the model. Several have placed tighter constraints on its parameters. The experimental picture is still unresolved, but the program of testing is active, well-funded, and genuinely competitive in a way that suggests the question is being taken seriously at the highest levels of experimental physics. What Diósi could not have known when he wrote down his equation in Budapest in 1987 was that nearly 4 decades later, a PhD student in Rome would take his model and Pearl's CSL model, hold them up to the light of a very specific question, and find in both of them a common prediction that nobody had extracted before. A prediction that time itself could not be perfectly smooth. That the tremor Bortolotti's team calculated was, in some sense, Diósi's equation leaving its mark on the universe's most fundamental parameter. Diósi is now in his mid-70s, still affiliated with the Wigner Research Centre for Physics in Budapest, still publishing, still arguing for the gravitational collapse hypothesis in conferences and papers and correspondence with colleagues around the world. He was a co-author on the Bortolotti paper. His name appears on the result that he, in 1987, could not have anticipated, the result that connects gravity, collapse, and a fundamental uncertainty in the nature of time. I find it moving, in a way I cannot entirely articulate, that the equation he wrote in a country still adjusting to the aftermath of one world and the uncertainties of another has ended up pointing at something this deep. That the solitary work of a theorist in Budapest, patient enough and precise enough to follow the mathematics wherever it led, arrived at a question that turns out to be among the most consequential in physics. Not all discoveries announce themselves with fanfare. Some of them wait, quietly, in the literature, for the moment when someone is ready to ask the right question. Let us step back. Let us take the widest possible view of what this all means. Because the story of the Flaw in time is not, in the end, a story about a calculation made in Rome in 2025, or about 2 equations developed independently in Budapest and Oxford 3 decades earlier. It is a story about something much older and much larger, about the single most consequential unfinished project in the history of science. For nearly a century, since the twin foundations of modern physics were laid in the 1910s and 1920s, theoretical physicists have known about a crack running through the centre of their discipline. On one side of the crack is quantum mechanics, the theory of the very small, of particles and fields and energy levels and probabilities, a framework that has been tested to more decimal places of precision than any other theory in the history of human inquiry. On the other side is general relativity, the theory of the very large, of gravity and space-time, and the cosmic geometry that governs the motions of planets, stars, and the universe as a whole, a theory so precisely confirmed that it predicts the existence of black holes and gravitational waves decades before we have the instruments to detect them. Both theories are, within their respective domains, essentially perfect, not approximately correct, not qualitatively right, quantitatively precise to a degree that would have seemed miraculous to the scientists of previous centuries. The standard model of particle physics, built on the foundations of quantum mechanics and quantum field theory, predicts the magnetic moment of the electron to 11 decimal places. The GPS system, corrected for the relativistic effects of general relativity, positions you to within a few meters anywhere on Earth. These are not modest achievements. They are the most successful predictive frameworks ever constructed by human intelligence, and they are fundamentally incompatible. The incompatibility is not merely technical. It is conceptual, deep, and in some ways philosophically troubling in a way that physicists have not always been comfortable acknowledging. The 2 theories disagree about the nature of space, the nature of time, and the nature of reality at the Planck scale, the scale of 10⁻35 meters and 5.39 times 10⁻44 seconds, both theories simultaneously predict their own breakdown. The conceptual clash around time is particularly stark. In quantum mechanics, time is a parameter. It is not an observable. You cannot build a Hermitian operator for time in quantum mechanics in the way you can for position, momentum, or energy. Time is simply the thing that the quantum system evolves against. An external backdrop, fixed and universal, unmarked by any quantum state and unaffected by any quantum process. This treatment is not accidental. It is built into the mathematical structure of the theory at the foundational level. In non-relativistic quantum mechanics, this is unproblematic because Newton's mechanics also treated time as an external parameter. But when you try to combine quantum mechanics with special relativity, you need to treat space and time on the same footing, and immediately the special status of time as a parameter begins to look awkward. And when you try to combine quantum mechanics with general relativity, where time is a physical, dynamic dimension that curves and stretches, and in principle can be measured with instruments that are themselves subject to general relativity's effects, the situation becomes almost paradoxical. The Wheeler-DeWitt equation, derived in the late 1960s by John Archibald Wheeler and Bryce DeWitt as the first serious attempt to quantize general relativity, produced an immediate and deeply disturbing result. The equation describing the quantum state of the entire universe, the universal wavefunction, has no time variable. The equation is static. It does not evolve. The quantum state of a universe that includes gravity is frozen. Time disappears entirely. This is the problem of time in quantum gravity, and it is not a minor technical difficulty. It is a conceptual crisis that cuts to the heart of what physics means. If the fundamental equation describing the quantum state of the universe has no time in it, if the universe at the deepest level of description is timeless, then where does time come from? Why do we experience it? Why does it move? Why does it have a direction? Various answers have been proposed over the decades. The relational time approach associated with Carlo Rovelli and Lee Smolins' loop quantum gravity program argues that time is not fundamental at all, that it emerges from correlations between subsystems of the universe in the same way that temperature emerges from the average kinetic energy of molecules. There is no absolute time. There is only the relative timing of events with respect to each other. Julian Barbour, in his book The End of Time, has taken this further, arguing that time is entirely illusory, that what we call time is a trajectory through a space of possible configurations, and that the apparent flow of time is a feature of how we experience this trajectory, not a feature of the trajectory itself. Sean Carroll at the California Institute of Technology has argued from the opposite direction. That time is real, that it has a direction because of the low entropy initial condition of the universe, and that the apparent problem of time in quantum gravity arises from a misunderstanding of how the Wheeler-DeWitt equation should be interpreted rather than from a genuine absence of time. None of these proposals has been confirmed. None of them has been falsified. They are theoretical frameworks, not experimental conclusions. The problem of time remains, after 60 years of sustained effort, open. But here is what makes the Bortolotti result consequential within this landscape. Spontaneous collapse models, and specifically the result that they predict a fundamental uncertainty in time, offer something that the purely theoretical approaches to the problem of time do not. They offer a physically testable prediction. Not today, the effect is far too small for current technology, but the form of the prediction is concrete, mathematical, and falsifiable in principle. If future technology ever reaches the precision required to probe the scale of space-time uncertainty that Bortolotti's team calculates, there are specific quantitative predictions to test, not philosophical proposals, equations. This matters because the history of physics contains several moments at which apparently insuperable theoretical conflicts were resolved not by more theorizing, but by experiments that forced the theorists' hands. The ultraviolet catastrophe, The failure of classical physics to correctly predict the emission spectrum of a black body was not resolved by philosophical argument. It was resolved when Planck found an equation that matched the data, and then spent years trying to understand why the equation worked. The resolution turned out to be quantum mechanics. The problem of the ether, the medium through which light was thought to propagate in the 19th century, was not resolved by theory. It was resolved when Michelson and Morley found, in their 1887 interferometer experiment, that the ether did not exist. Special relativity came later as an explanation for the experimental null result. The problem of time may follow the same pattern. We may not resolve it through purely theoretical debate about interpretations. We may need to find an experimental signature, a fingerprint, of whatever the correct theory of quantum gravity turns out to be. And Bortolotti's result suggests that one candidate fingerprint is a fundamental limit on clock precision, a tiny tremor in time that would be, if we could ever measure it, a direct signature of the gravitational collapse mechanism that his equations describe. But there is a deeper, darker layer to this story, because the implications of the Diósi-Penrose model, if correct, do not stop at clock precision. They reach into questions about the stability of matter, the thermodynamics of the universe, and ultimately the relationship between consciousness and physical reality, in a way that has made some physicists deeply uncomfortable and others profoundly excited. The reason is energy. Spontaneous wavefunction collapse, as described by both the CSL model and the Diósi-Penrose model, is not energy conserving in the standard sense. The collapse events inject a tiny, continuous input of energy into physical systems, a consequence of the stochastic noise field that drives the collapse. For any individual particle, this energy input is fantastically small, but integrated over all the particles in the universe. Over all the time the universe has been evolving, the total energy input from spontaneous collapse becomes significant. Where does this energy come from? And where does it go? This is the energy problem of spontaneous collapse models, and it is one of the reasons the models have been met with persistent skepticism in some quarters of theoretical physics. Standard quantum mechanics conserves energy exactly. Standard quantum mechanics is consistent with the first law of thermodynamics, the foundational principle that energy is neither created nor destroyed. Spontaneous collapse models, as originally formulated, appear to violate this principle, at least in the long run. Dissipative versions of the CSL model have been developed, modifications that introduce an additional damping mechanism to ensure finite energy in the long run, but these modifications come at the cost of additional free parameters and additional physical assumptions. The question of whether spontaneous collapse models can be made fully consistent with thermodynamics remains open. And it is relevant to our story because the energy injected by collapse events is not just a bookkeeping problem, it is in principle observable. It would produce a tiny but non-zero heating effect in cold atoms, in cryogenic materials, in any system that has been cooled as close to absolute zero as possible. Experimental searches for this heating signature have placed increasingly tight constraints on the parameters of both the CSL and Diósi-Penrose models. So far, no positive detection has been made, but here is what is remarkable about the situation. The constraints placed by energy measurements and the constraints placed by the time uncertainty result are complementary. They come from different experimental directions and probe different parameter regimes of the models. The time uncertainty prediction is not directly constrained by any existing experiment. It reaches into a precision regime that no clock has approached. The energy measurements probe the collapse rate parameters from a thermal physics direction. Together, they map out the boundary between where the models might be correct and where they must be wrong. Every scientific theory has this quality, a perimeter of testability, a frontier where the predictions meet the data and either survive or fail. The Diósi-Penrose model and the CSL model are approaching their frontier. The experiments are getting better. The theoretical predictions are getting more precise. The next decade will, almost certainly, produce decisive results one way or another. And if the models survive, if the experiments confirm the spontaneous collapse prediction, if we detect the energy signature or push clock precision far enough to see the time uncertainty or find some other signal that no standard quantum mechanics can explain, then the implications are civilization level in scope, because a confirmed spontaneous collapse model would not merely solve the measurement problem, it would establish a physical mechanism connecting quantum mechanics and gravity. It would identify, for the first time, an experimental signature of quantum gravity, the deepest theory physics has been searching for. It would resolve the problem of time by showing that time does indeed emerge from a quantum gravitational process, that the smooth flow of time we experience is the macroscopic outcome of countless microscopic collapse events, each one infinitesimal but collectively producing the unidirectional, irreversible river of time that Eddington named almost a century ago. It would, in effect, explain why yesterday happened before today, and it would mean that Lajos Diósi, writing his equation in Budapest in 1987, had inadvertently written the first paragraph of the deepest story in physics. It would be dishonest and scientifically indefensible to present the Diósi-Penrose model and the CSL model as the consensus view of the physics community. They are not. They are minority positions within the field of quantum foundations, serious, well-developed, actively investigated minority positions, but minority positions nonetheless. The objections to spontaneous collapse models are numerous, technically sophisticated, and taken seriously by some of the most rigorous physicists currently working. Let us go through them honestly, one by one, because the credibility of the science demands it, and because the objections themselves illuminate, perhaps more clearly than the affirmations, what is really at stake in this debate. The first and most persistent objection is experimental. Both the Diósi-Penrose model and the CSL model have been constrained, over the past 2 decades, by an increasingly comprehensive set of precision experiments. These experiments fall into several categories. There are cold atom experiments, in which clouds of atoms cooled to, within fractions of a microkelvin of absolute zero, are held in magnetic traps and observed for evidence of anomalous heating or positional diffusion, signatures of the stochastic collapse noise that both models predict. There are crystal experiments, in which the thermal noise in cryogenically cooled mechanical oscillators is measured with extraordinary sensitivity, looking for any excess noise that cannot be explained by standard thermal physics. And there are optomechanical experiments, in which levitated nanoparticles are cooled to near their quantum ground state, and observed for evidence of wavefunction collapse effects that would prevent them from maintaining a coherent quantum state. The current experimental situation is that these experiments have placed increasingly tight constraints on the parameters of both models, eliminating regions of parameter space that the models had previously been free to occupy. A 2022 survey of experimental constraints, reviewed in Quanta magazine under the somewhat unflattering headline "Physics Experiments Spell Doom for Quantum Collapse Theory," suggested that the most natural parameter values for the CSL model had been excluded by experimental data, that the theory's predicted noise level at the values GRW had originally proposed was inconsistent with the measured results. However, and this is a crucial qualification, the exclusion of the original GRW parameter values does not exclude spontaneous collapse models in general. The models have free parameters, and within the ranges of those parameters that remain experimentally viable, the models are still consistent with all known data. The constraints narrow the viable region. They do not eliminate it. The experimental situation is better described as increasingly informative rather than definitively falsifying. The second objection is theoretical, and it is the one that Roger Penrose's critics have most persistently raised. The Diósi-Penrose model, as originally formulated, runs into a technical problem involving the energy scale of the collapse process. The Penrose estimate for the collapse rate, based on the gravitational self-energy of the superposition, turns out to depend sensitively on what you assume about the internal structure of the superposed object. For a smooth mass distribution, the result is one number. For a distribution of discrete point charges and nuclei, the result is very different, and in the point particle limit the collapse rate diverges. It becomes infinite, which is physically nonsensical. Diósi himself has been aware of this problem since the early 1990s, and several variants of the model have been proposed that regularize the divergence by introducing a minimum length scale below which the mass distribution is treated as smeared out. The most natural such length scale is the nuclear radius, the physical size of the atomic nucleus, and with this regularization, the model gives finite, consistent predictions. But the need for regularization means the model is not quite the clean, parameter-free theory that Diósi's original 1987 paper aspired to be. A length scale has been introduced, and its physical meaning is not fully understood. The third objection is the most philosophically fundamental, and it is the one that has generated the most heated debate within the quantum foundations community. Spontaneous collapse models are nonlinear. They modify the Schrödinger equation by adding a nonlinear term, the stochastic noise that drives the collapse. Nonlinearity in quantum mechanics is in general an extremely dangerous ingredient. It is well known that nonlinear quantum mechanics, taken seriously, allows for the possibility of superluminal signaling, the transmission of information faster than light, in violation of special relativity and of the causal structure of space-time. Proponents of spontaneous collapse models have argued, persuasively, that their specific form of nonlinearity does not permit superluminal signaling because the stochastic noise is fundamentally uncontrollable. It cannot be used as a channel for deliberate information transmissions because no one can predict or manipulate what the noise will do. The randomness itself is what preserves the no-signaling condition. But the argument is subtle, and some theorists have remained skeptical that the non-signaling condition is maintained in all circumstances, including situations involving relativistic quantum field theory rather than non-relativistic quantum mechanics. The relativistic extension of spontaneous collapse models is, in fact, the front line of the theoretical program. Non-relativistic CSL was developed in detail in the 1980s and 1990s and is internally consistent, but a fully covariant, Lorentz invariant version of spontaneous collapse, one that respects special relativity and can be extended to quantum field theory, has proved difficult to construct in a way that is both mathematically consistent and physically sensible. Several proposals exist, but none has been universally accepted as the relativistic extension of the model. This is a genuine weakness of the program, and one that its proponents acknowledge. The fourth objection is the one that strikes me personally as the most compelling, and it is the one that connects most directly to the new result of Bortolotti and his team. It concerns the energy problem we described earlier. Spontaneous collapse models predict that the stochastic collapse noise continuously injects energy into physical systems. At the level of individual atoms, this energy is fantastically small, but at cosmic scales, over the lifetime of the universe, the total energy injected by spontaneous collapse into all the matter in the observable universe is substantial. Where does it come from? Within the Diósi-Penrose framework, the answer is, at least gesturally, available. The energy comes from gravity, from the same space-time fluctuations that Bortolotti's team used to derive the fundamental time uncertainty. Gravity is, in a sense, the noise source. The quantum gravitational fluctuations of space-time drive the collapse, and the energy injected into matter by the collapse is drawn from the gravitational field. This is a consistent picture in its broad outlines, but it has not been made precise at the level of detailed calculations. The gravitational field's role as a cosmic energy reservoir for spontaneous collapse is still a theoretical sketch rather than a worked-out theoretical framework. Bortolotti's paper represents, in part, a step toward making this sketch more precise. By establishing a quantitative relationship between the CSL collapse parameters and the space-time metric fluctuations of the Diósi-Penrose framework, the paper provides a bridge between the two models that makes the energy accounting more tractable. It is not a solution to the energy problem, but it is a step toward the tools that a solution will require. The fifth, and perhaps most uncomfortable objection, is not about the physics of the models themselves, but about their entanglement with ideas about consciousness. Roger Penrose's involvement in spontaneous collapse theory comes with a theoretical appendage that has made many physicists uncomfortable. The proposal, developed with anesthesiologist Stuart Hameroff, quantum collapse events inside microtubules in neurons are responsible for conscious experience, the orchestrated objective reduction, OR hypothesis. This proposal is, to put it mildly, not widely accepted. It requires coherent quantum superpositions to exist in the warm, wet, noisy interior of living neurons for biologically significant timescales in a thermal environment that most physicists consider inimical to quantum coherence. The experimental evidence for quantum effects in microtubules is at best highly contested. The danger is that the legitimate physics of the Diósi-Penrose collapse model, the quantitative testable predictions about collapse rates and energy signatures, and now time uncertainty, is sometimes judged unfairly by association with OR, which is a far more speculative proposal at the intersection of neuroscience and quantum physics. The measurement problem is a real problem in physics. The gravitational collapse hypothesis is a real hypothesis with testable predictions. OR is a much more speculative extension of those ideas into the domain of consciousness, and its empirical status is separate from, and considerably weaker than, the status of the collapse model itself. Diósi has, over the years, been careful to distinguish between the two aspects of Penrose's work, endorsing the gravitational collapse physics while maintaining more distance from the consciousness hypothesis. His co-authorship on the 2025 paper reflects this distinction. The result they derived concerns time and clocks, not neurons and awareness. The current state of affairs, then, is this: spontaneous collapse models are alive, active, and generating increasingly precise experimental predictions. They have survived 2 decades of increasingly sensitive experimental tests by remaining within the experimentally viable parameter space, though that space is shrinking. The theoretical program is incomplete. The relativistic extension remains a challenge. The energy accounting requires more work. The divergence problem in the Diósi-Penrose model requires regularization. But the program is not dead, it is not falsified. And in November 2025, it produced a result that even its critics had to acknowledge was theoretically significant. A precise quantitative prediction of a fundamental limit on the precision of time itself. The prediction is in physical review research. It has been reviewed by referees. It is in the literature. And it says something that no standard quantum mechanics, no many worlds interpretation, no Copenhagen or relational or information theoretic approach to the measurement problem could predict. That time has a flaw. That the universe's most reliable metronome ticks against a background that is not perfectly smooth. That the arrow of time, the deep, irreversible asymmetry between past and future that Eddington named in 1927, may be stamped into the very fabric of temporal measurement itself at a scale too small to touch, but too fundamental to ignore. There is a question I have been carrying through all of this research that I want to address directly. Critics of spontaneous collapse models sometimes characterize them as entities that are technically alive but scientifically marginalized. Theoretical curiosities that persist in the literature through the personal investment of a small community rather than through compelling evidence. This characterization is, I think, unfair. The measurement problem is not marginalized. It is acknowledged by the mainstream of theoretical physics as a genuine open problem. The various competing solutions to it, many worlds, relational interpretations, Bohmian mechanics, spontaneous collapse models, are all seriously evaluated by serious people. None has emerged as the consensus answer. The field is genuinely open. What the 2025 result adds to this open field is something specific, a prediction that distinguishes spontaneous collapse models from all other approaches. Not a vague qualitative difference, but a quantitative, mathematically precise prediction about a specific observable quantity, the precision of clocks operating at extreme timescales. This is exactly the kind of distinguishing prediction that physics needs in order to make progress. And whether the models are ultimately confirmed or falsified, the act of deriving this prediction is itself a contribution to the program of turning the measurement problem from a philosophical debate into an experimental science. One further complication deserves full treatment because it connects the Bortolotti result to the broadest possible landscape of physics. The same year that Bortolotti's paper appeared in Physical Review Research, a separate group at Perimeter Institute in Canada published a paper proposing a theory of emergent time based on wavefunction collapse in general relativity, a framework in which time itself is not a fundamental ingredient of the universe, but emerges from the collapse process as a kind of byproduct. This paper, published on the RxIV in October 2025, and subsequently appearing in the Journal of High Energy Physics in April 2026, proposed that quantum states which violate the constraints of general relativity represent instances of time, that the collapse of such states toward diffeomorphism in variant configurations generates the monotonic increase of a scale factor that functions as a cosmic clock. In other words, time in this proposal is what wavefunction collapse produces, not the backdrop against which collapse occurs, but the product of it. Time does not exist prior to collapse and collapse occurs within it. Rather, collapse is what generates time in the first place. If this is right, and it is a very big if, it would mean that the tremor in time that Bortolotti's team calculated is not a flaw in an otherwise smooth background. It would be more fundamental than that. It would mean that the entire fabric of temporal experience is assembled, moment by moment, from the accumulated outcomes of innumerable collapse events, each one contributing a quantum of temporal experience to the flow we call history. The tremor would not be a blemish on the surface of something smooth, it would be the texture of the thing itself. We stand in 2026 at a peculiar moment in the history of time, not in the sense of historical juncture, though this moment has its own significance, but in the literal physical sense. We understand more about time than any generation of humans has ever understood. We can measure it to a precision that staggers the imagination. We know it is relative, that it bends under gravity, that it ran differently in the early universe, and would run differently still at the boundary of a black hole. We know that it has an arrow, that the arrow points from low entropy to high, and that the arrow was set at the initial conditions of the Big Bang, in a state so impossibly special that we have not yet explained why it existed. We know all of this, and we still do not know what time is. The result from Bortolotti's team adds a new layer to this not knowing. It says that time may be subtly imperfect, that the smoothness we assume at the foundational level may be an approximation, that below the scale of anything we can currently measure, time may have a texture, a grain, a tremor that connects it to the unresolved problem at the centre of quantum physics. What comes next? What does the discovery of this flaw, theoretical, not yet experimental, but mathematically precise and scientifically significant, imply for the next chapters of physics? The immediate experimental program is well defined, even if its timescale is uncertain. The NIST Ytterbium optical lattice clock that set the record of 1 second per 300 billion years is, by the standards of what the Bortolotti calculation demands, still many orders of magnitude away from the relevant precision. The time uncertainty that spontaneous collapse models predict is of order 10⁻33 seconds at the current parameters of the models. The most precise clocks in existence are sensitive to fluctuations at the level of roughly 10⁻19 seconds. The gap is 14 orders of magnitude. That is not a gap that will be closed in the next decade or the next century with any technology that currently exists. But the history of precision measurement in physics is a history of gaps that seemed unbridgeable until they weren't. In 1960, when the first cesium beam atomic clocks were developed, an accuracy of 1 part in 1011 was a remarkable achievement. Today's optical lattice clocks achieve 1 part in 1018s, an improvement of 7 orders of magnitude in 60 years. If that rate of progress were to continue, which is a big assumption since precision measurement tends to slow as it approaches fundamental limits, then 14 additional orders of magnitude would require roughly 120 years. A long time. But not forever. More practically, the experimental program does not depend solely on direct measurements of time uncertainty. The complementary approach, searching for the energy injection signatures of spontaneous collapse in cryogenic experiments, is already underway and already producing results at sensitivities that probe the viable parameter space of both the CSL and Diósi-Penrose models. The QUEST experiment at the Wigner Center in Vienna, the ATRAP collaboration at CERN, the levitated optomechanics experiments at groups including those at Delft, Vienna, and Caltech. All of these are approaching sensitivities that will either detect spontaneous collapse or eliminate large swaths of the remaining viable parameter space. There is also a third experimental direction, perhaps the most audacious, that involves quantum entanglement and gravity simultaneously. The Bose-Marletto-Vedrel (BMV) proposal, made in 2017 by Sugato Bose at University College London and independently by Chiara Marletto and Vedrel, proposed an experiment in which 2 quantum superpositions of massive objects are brought into close proximity and allowed to interact gravitationally. If gravity can entangle the 2 systems, if the 2 superpositions become quantum mechanically correlated through their gravitational interaction, then gravity must itself be a quantum field capable of mediating quantum correlations. This would be, in effect, the first direct evidence that gravity is quantized. The BMV experiment has not yet been performed. It requires levels of mass superposition and isolation that remain beyond current technology, but it is actively being pursued by several experimental groups. And its result, when it arrives, will be directly relevant to the question of whether the Diósi-Penrose model is on the right track. If gravity can entangle quantum systems, then the gravitational mechanism for wavefunction collapse becomes physically credible in a new and direct way. The stakes of these experiments cannot be overstated, not in the sense of technological application. The practical implications of detecting spontaneous collapse are not obvious, since the effect is so small that it does not affect any existing technology. The stakes are epistemological. They are about what the universe is. They are about whether the standard quantum mechanics we have been using for a century as our window onto reality is complete, or whether there is a deeper physics underneath, a physics in which collapse is not mysterious, in which the measurement problem is solved, in which the arrow of time has a dynamical explanation rather than merely a statistical one, and in which the flaw in time that Bortolotti's team calculated is not an anomaly but a feature, a fingerprint of quantum gravity, visible in principle in the precision of every clock. This is the frontier. This is where the physics is being done right now, in laboratories and on whiteboards, and in papers published in refereed journals and argued over at conferences. Not in the clean, settled domain of established science, but in the contested, uncertain, disputatious territory where the known ends and the unknown begins. The question of what time is has been central to human thought for as long as humans have been capable of thought. St. Augustine, writing in the 5th century, offered the most honest assessment in the history of philosophy. If no one asks me what time is, I know. If I want to explain it to one who asks, I do not know. Isaac Newton tried to settle the question by defining time as absolute, true, and mathematical, flowing equably of itself, from its own nature, independently of anything external. Einstein demolished this definition in 1905, replacing it with something relative, personal, dependent on the observer's motion and the local strength of gravity. quantum mechanics added another layer of strangeness, treating time as a classical parameter in a theory that insisted everything else was quantum. General relativity made time dynamic and physical in a way that quantum mechanics could not accommodate. And now, from the intersection of these two unreconciled frameworks, comes a suggestion that time may have a tremor, not in the abstract philosophical sense, but in the concrete, measurable, physical sense. A tremor rooted in the gravitational dynamics of wavefunction collapse. A tremor that, if the theory is right, is present in every measurement of time ever made by any instrument at a level too small to detect but too fundamental to dismiss. The next generation of physicists, the ones who are today learning quantum mechanics from textbooks, or running simulations in graduate school, or doing their first experiments with cold atoms in undergraduate laboratories, they will inherit this question. They will have better clocks than we have. They will have better experiments. They will have theoretical tools that do not yet exist, mathematical languages adequate to problems that currently defeat us. And they will perhaps resolve the question that this generation can only sharpen, not whether time has a flaw. We now have good reason to think it does, but what the flaw means, what it tells us about the deepest structure of reality, whether it is the signature of a theory that will finally unite quantum mechanics and gravity, or whether it points towards something stranger still, a physics so different from anything we currently imagine that the concepts of quantum mechanics and general relativity will both seem like approximations to something more fundamental. The way Newtonian mechanics now seems like an approximation to relativity. The answer is not ours to know. Not yet. There is a particular quality to the silence that descends after a very large question has been asked. Not the silence of an answer which resolves tension and releases breath, but the silence of a question that has grown larger than the room it was asked in. The question of what time is, and whether it trembles, and whether the trembling means that our two greatest theories of nature are already leaving their fingerprints on the universe's most fundamental parameter. This is a question of that kind. It does not resolve, it expands. What strikes me most in all of this is not the technical result. The calculation is remarkable, but calculations are made every day in physics departments around the world, and most of them are never heard of again. What strikes me is the continuity of human puzzlement across time. Eddington naming the arrow in 1927, Schrödinger imagining his cat in 1935, Girardi, Rimini and Weber sitting with their equations in Trieste in the 1970s, asking why measurement caused collapse, Diósi in Budapest, finding an answer that involved gravity, Penrose in Oxford, arriving at the same answer by a different path, and Bortolotti in Rome, young enough to ask a question that the field had been circling for decades without quite landing on, and finding in the answer something that recontextualized all of the above. Time is not merely the thing we measure. It may be the thing that physics has been arguing about, in disguise, for the entire length of the quantum era. The measurement problem is a problem about time, about why collapse is irreversible, about why the arrow exists, about why the past is definite and the future is not. The problem of time in quantum gravity is a problem about whether time is fundamental or emergent, whether it is the stage or the performance. The second law is a problem about time, about why entropy increases, about why yesterday was more ordered than today, about why the universe began in a state so special that it allowed a temporal arrow to emerge. All of these problems point at the same wound in physics, and what Bortolotti's result suggests is that the wound may be small, not civilizationally catastrophic, not visible to any instrument in the near future, but real, a tiny flaw built into the nature of time at a level so deep that only the most extreme of precision measurements could ever hope to detect it. There is something oddly comforting about this, not because flaws are good, but because the presence of the flaw tells us that the question is not merely philosophical. It tells us that the disagreement between quantum mechanics and gravity is physical, not merely conceptual. It tells us that the universe has left a trace of its own incompleteness in the very thing it uses to mark the passing of events. And traces, in physics, are how every discovery begins. Science does not give us endings, it gives us measurements. And from measurements it gives us questions, and from questions it gives us the next experiment. The tremor in time that Bortolotti calculated is perhaps the first measurement of a question that has no current answer. It is a data point from the frontier, a pixel in an image whose subject we have not yet identified. We are the generation that found the flaw. What we do not yet know is what we have found the flaw in, whether time is the surface of something deeper, whether the trembling when we finally understand it will sound like the grinding of two great theories against each other, or like something older, stranger and more beautiful. Whether the arrow of time is a feature of the equations, or of the universe, or of us, the question does not need an answer today. It needs to be kept alive long enough for someone younger and braver to carry it further. Time is not perfect, and the search for what that imperfection means has only just begun.